Thanks. Can everyone hear me all right? Okay. So who saw my CoreOS introduction earlier this week? Okay, great. So that's really good because I will not be spending a lot of time talking about what we're actually doing in the tutorial. It'll be mostly hands-on on the command line. And so I will be giving some introduction to the components as we use them within the tutorial, but it's not going to be in-depth. There'll be a video of my my CoreOS introduction from earlier this week uploaded to the conference website. So you can follow along with the tutorial. You may be slightly confused, but the introduction will kind of clear up any lingering questions. So I'm the CTO and co-founder of CoreOS. Originally, this talk was submitted by Kelsey Hightower. So if you have any praise, it's at Brandon Phillips. And then if you have any complaints or critiques of this talk, it's at Kelsey Hightower. That'll be where you'll want to send those, any of those things. And then, yeah, that's my GitHub profile photo, if you have ever seen me on the internet before. I know I appreciate it when people use their GitHub profile photos on their presentations because I can't often recognize faces, but I've seen those little gravicons so many times that it's instant recognition. So, right, so I'm going to just quickly give some people some context of what we're doing here. So CoreOS, the goal here is to build a data center as a computer. Essentially, we want to have a number of virtual machines or physical hosts that are resilient to and have a number of virtual machines and physical hosts acting together to run applications, and we want to design for resiliency against individual hosts failing. So I'll exit the presentation, and then we can start dropping down to the command line stuff. This tutorial is laid out on a README file on github.com/Phillips/CoreOS ops tutorial. Can everyone see the font size on the shell? Okay. And so there's a few prerequisite tools that you'll need to build if you don't have them on your laptop. And you'll need a working Go environment. Since we're really short on time and this lecture hall is gigantic, I'm not going to really wait for anybody. So sorry. What I recommend is that you use this README file as your Cliff Notes if you want to try this at home, but you mostly follow along with me because this tutorial is rather short. Yes?
I'm just going to, it not only requires a working Go environment, but you need to have at least Go 1.3.
Yeah. Yeah. There are binary releases of these things, but I couldn't anticipate what Linuxes or OS X's or Windows people were running, and it just complicated everything. So where we'll start is we'll start up a single virtual machine that will be our control machine for this cluster. And I'm using Google Cloud, Google Compute, for all this, for all the VMs that we're spinning up. And what I'm doing here with this command line tool is Google has an SDK. It has a command line tool called gcloud, and I'm specifying that I'd like to turn on a CoreOS instance that's running a fairly recent version of CoreOS. And then I'm sending in some user data to do initial configuration of that host. So the user data is a YAML file. It is classically, or what it is it's called a cloud config, and this has been adopted by a number of different operating system vendors, and it's essentially a way of doing initial configuration of a virtual machine as it does its first boot. So why don't we take a look at that cloud config and how we're configuring this control node. Can everyone still read the font size? Because it's really important that you actually be able to see the text. Okay. So this is a YAML file. And let me see if I can turn this on. No, never mind. So this YAML file does a few things. First, it turns on Fleet and sends in a little bit of metadata saying that the role of this virtual machine is a control server, meaning that this virtual machine will be running an API service that we talk to throughout this tutorial. So this will be the primary IP address into the cluster because you have to talk to some some API or some API and some IP address. So we'll use this one VM as the canonical thing. Obviously, all the APIs we're talking to can be leader elected and they can fail over automatically and that sort of thing. It's just for convenience we're talking to this one server. We're also telling this host that it needs to be running etcd. Etcd is a key value store that is designed to tolerate individual host failures. And this is the backbone for various schedulers and tools that we'll be using. So the schedulers of Kubernetes and Fleet use etcd, and then also the scheduler of our overlay networking system called Flannel will also be using etcd. So this control node will be hosting the etcd cluster. We're only using a single member etcd cluster in this tutorial, but etcd is designed to be ran on 5 to 7 machines for host resiliency. Again, this is a tutorial, so we're doing the simplest possible thing. And so we start etcd, we start Fleet, and then we also start a service called systemd journal gateway. Later in the demonstration, we'll be exporting all the journal entries off of the host onto a hosted service. All right, so that's the initial configuration. Essentially, we're bringing up a single machine that's running etcd, Fleet, and then has a API endpoint for exporting log files. Everyone on board? Yes? Okay. So it looks like gcloud is having a good day. So everything came up really fast. I got rate limited earlier. Don't spin up lots of machines. You will get rate limited. So what we'll do first is, for convenience, we want to use a few command line tools from our local laptop. The first will be etcd-ctl. This is a command line, or etcd-ctl. It's a command line tool that gives you easy command line access to the etcd key value store, so you can set keys and get keys, etc. So we'll set up we need the actual IP there. So we'll set up a simple SSH proxy to this control host. And then we'll just blindly trust the internet to give us public keys without doing any verification. Don't do this at home. Yes, I always trust the internet. Right, so what this did was it's forwarding all the etcd that's running on the control host, the etcd port, which is 4001. We got an actual IETF assigned port recently, so but we just chose that at random when we started the project. But we're forwarding that to our laptop. So now we are able to do things like etcd-ctl set foobar. Okay, so we're able to talk to the etcd server that's running on this control host, right? And then obviously we can get keys back out. So we're able to do things with this etcd cluster. All right, the other piece is that we'll be wanting to have access to the Kubernetes API later in the tutorial. So we'll go ahead and set that up too. Oops, I'm bad at bash. So this is another SSH proxy that's going to be port 8080 to our local host. And then the last bit is that we will want access to Fleet, and Fleet's a very simple scheduler that's designed around creating something that looks like systemd, but is distributed across a lot of hosts. So systemd is an init system for a single host. Fleet is an init system for multiple hosts. And you interact with it in a very similar way to systemd. So we will say that this control host will be the Fleet-ctl tunnel. So now we can do things like Fleet-ctl list units, and again, just blindly trust the internet. Okay. All right, so there's nothing running on the cluster right now because it's a brand new cluster. Great, and then the last bit is that we have, since I didn't want to bother setting up DNS for the tutorial, there's a few configuration files and configuration parameters that are templated within this Git repository that we're working out of. And so I'm just going to run a quick sed to get the to configure all that stuff. Essentially, it's just so that the worker nodes. So there's a control node, which is hosting all the APIs and stuff, and then there's going to be an n number of worker nodes. And so those worker nodes know where to get information about the cluster. So we will do a quick sed, and then, what did I do wrong? Oh, /g. Okay, so now if we do git diff, we should see that a bunch of stuff has been changed. So essentially where to find the etcd cluster, where to talk to the APIs, et cetera, in these service files. Great, everyone on board so far? So we have a single host, and we're able to talk to it via a couple of APIs. All right, so the next piece that we want to accomplish here is that we want to have networking between the hosts. So we wrote a piece of software called Flannel, and what Flannel does, it's an overlay network fabric. Get the joke? It's Flan. All right, so what Flannel does is it creates a UDP encapsulated overlay network that you can run fairly inexpensively on VMs. So the problem that we're solving is that a lot of people have infrastructure where each host has a single IP, but our opinion and the opinion of projects like Kubernetes is that it's really convenient if each container, each application that's running on your in your infrastructure has its own unique IP instead of trying to do port mapping business. And so what Flannel does is that it essentially creates a logical route table between a virtual machine that has IP A and then another virtual machine that has IP B, and then it overlays a 10 dot or whatever sort of subnet network you want on top of those two things. And so each host gets, say, a /24 or /16, however you want to allocate networks. And so in this case, what I've done here is I'm storing the configuration of the Flannel network, saying that I'm going to use 10.244 as a /16, and Flannel will assign subnets out of that IP range to each individual host. And then as things come out of that host, it'll route to other 10.244 networks or other 10.244 addresses between and to the appropriate virtual machine. Everyone get how that works? Would a diagram help? Everyone, I'm seeing some nods, so I think everyone gets it. So we set that configuration because the actual worker nodes are going to want to bring up Flannel and essentially do this subnet assignment to themselves. So what I'm going to do here is we're going to spin up 5 worker nodes that are going to connect to our control node. And these worker nodes, I'll just start it because the Google Cloud can take a few seconds. But they have a similar to the control node. They have a cloud config that describes the initial state. Essentially, they're running etcd. They're running Fleet just like the other members. So they'll have an etcd server and they'll have a Fleet server running on the host. This is a little ugly. We cleaned it up recently, and it actually uses containers now. But that was like a week ago, and I forgot to update the tutorial. But essentially, Flannel is a daemon that runs in a container that does this IP assignment and then tells the Docker engine you need to use this this network interface called Flannel 0, and you need to assign IPs to the containers out of this IP range. And then we have to configure Docker. Again, this is stuff that you don't have to do anymore as of a couple weeks ago within CoreOS, but this is muck to set up Docker appropriately. All right, so it's bringing up etcd, Docker, and Flannel on each of these worker nodes, hopefully. Right, so the 5 worker nodes came up on Google Compute. They have external and internal IPs. Great, so we should now, since they brought up Fleet and they talked to the control node, when we do Fleet CTL list machines, we should see 5 members within that cluster. Perfect. Well, actually 6, because the control node added itself also. And you'll notice that the nodes have particular roles. So there's role equals node, meaning that they're just regular working machines, and then there's role equals control, which means that that's our control server. And you can use these roles. Essentially, it's just an arbitrary key value pair of labels, but you can use this metadata to say where work lands. Obviously, you don't want your super heavy Hadoop workload or whatever to land on the control node, because the control node has other important things to be doing. But this is how you can start to plan out the roles of different things in the infrastructure and land work at the right place. Yeah.
How big of nodes have two roles? Like, could a machine be like a control and node?
Yeah. So the labels have to be unique. So you can have role equals control, and then environment equals production or whatever, but it has to be a unique set of things. So if you wanted to have multiple roles, you'd want role equals control, comma, node or something. And your application needs to be aware of that sort of stuff and how it's using that API. All right. Great. So why don't we take a look at what actually happened in etcd with all this? So you remember that we use etcd-ctl to write into the etcd key space, the configuration, the shared configuration of how the network should be laid out for Flannel. So what is also stored in etcd is essentially each of these hosts does a master election on some subset of the IP range that we've allocated. So you'll notice that people have done master elections on these /24s. So .39, .22, et cetera, et cetera. And so what's happening is that the Flannel service running on each of these hosts periodically is saying, hey, I'm a host, I'm still alive, don't give this lease away. It works very much like a DHCP lease, only since it's deciding where IP traffic is routed, it needs to be fully consistent, because you want to make sure that those packets that you're routing to the hosts are actually going to the host that you expect. So etcd-ctl get, and then there should be some metadata in there. I don't know why it's frozen, but because no sync. This flag no sync is because of the fact we're using an SSH proxy. But essentially, the metadata that's stored in that key is the public IP address of the host that is hosting that subnet, so we know where to route those packets to and decap them. So we encap them as they're exiting and decap them. All right. So why don't we look at how this actually looks in practice? So we'll SSH into one of the nodes, and then we'll SSH into the other node too. So that seems to be taking a while. And we'll run BusyBox on this host. I know for a fact that that is the incorrect command line. Oh, it actually worked. Hooray. So what we're running on each of these nodes, this is actually a really bad layout. Let me change this. All right. So what we're running on this machine here, if you can see the command line, is we're running BusyBox, and we're saying we want to use netcat. Let me run this other one. So we're running BusyBox. We're getting the IP address. You'll notice the IP address exists in that 10.244 range of the overlay network, and it is the .39 /24 subnet of that overlay network. Makes sense? And then we're running netcat listening on port 80 from this container. And then what we can do to just prove that all this in-cap craziness and master election of IP addresses is working is we can run netcat on the other side as a client. And then hopefully if I say, hello Auckland, woohoo! Yes! Round of applause. No. So the overlay network's working. We're running 2 containers that each have unique IP addresses in the environment, and they're able to talk to each other over TCP. Awesome. And so this is the basics of how the network can work. Obviously, you can not use flannel. Flannel is an option for people who have VMs or have infrastructure that has really flat networking, where you can assign multiple IP addresses to a single host. If you have SDN environments or whatever, you have to make Docker aware of that, and it's fairly straightforward. If you have things like what's the term? If you're using Google Compute, they actually allow you to assign multiple IPs to individual hosts, like thousands of IPs can land on a single VM. So if your network supports these sorts of things, you don't need something like Flannel. But in a lot of cases, people don't have these environments, so you need something like this to do this overlay. All right, everyone on board? Any questions so far? Been really quiet, everybody. No coughing or anything, so fantastic work. Thank you. All right, so this gets you set up in an environment where you have containers, you have a number of hosts, and we haven't really done anything that interesting quite yet. One of the questions that we do get asked quite a bit is that people would like to be doing things like log aggregation or service monitoring and that sort of thing. So I did want to go through and show how that sort of stuff can work on, let me see, hopefully I didn't lose my, there we go. And show how that sort of stuff can work. So there's a hosted service called log entries, and log entries is one of these things that can take over TCP your logs and export them off of a host. And so they have a API key based thing, and there's a container that takes the log entries agent and hooks it up to the systemd journal and exports your logs at runtime over the internet. So again, we use etcd to store this important configuration data of the API key. You could imagine wanting to encrypt this first. What other systems do, like there's an HTTP load balancer backed by etcd called Vulkan, and they have a pre-shared key. So each of the hosts has a key that's laid down on disk, or that the system administrator logs in when the process comes up and types in the password. And then that pre-shared key then is able to decrypt the TLS private certificates that are held in etcd. But that's left to the application to figure out how to protect their secrets if they're interested. Okay, so right, we set this token, and then we can start a global service. So one of the things that Fleet does is it enables you to run a service across all your hosts. So we'll take a look at this service file. Who here has used systemd, and written service files? Okay, so if you're a system administrator or a developer, the good news is that everything I'm about to say is extremely relevant, because everyone will be using systemd soon enough. Welcome to the future. So it's actually not that scary and bad. The internet, it turns out the internet has this tendency to overblow arguments into hyperbole. So what systemd does is very similar to how things like sys5 init or upstart have worked. So in the past, we've had things like Apache 2 start, and then upstart came along and it became like start Apache 2. And then systemd came along and completely revolutionized the world, and now it's systemctl start Apache 2. And this is what a lot of people are super upset about. And then along with that, one of the big problems with things like etc initd Apache 2 is that it's this 400-line bash script that does a bunch of random stuff. And it implements this logic that every daemon has to implement of saving a PID file somewhere, and then checking configuration files, and then checking that PID file and hupping the right thing if somebody does a reload. Just kind of all this boilerplate stuff. And so what systemd has done is it's a static file that doesn't allow for any sort of Turing completeness at all. You say things, I'll just delete some of this, but you can say things like exec start pre, so things that should happen before, and then you can say other things like, I want you to run this single binary. It doesn't allow for any sort of Turing complete stuff. But in the case, so a service file can be as simple as, we'll write one really quick. It can be as simple as this. We'll do something really useful, like user bin sleep, 5,000 or 4,000. And so this is a fully compatible service file. This is all you need to start a service. And so this can be, a Python script, this can be bash, whatever. And systemd does a number of nice things, like it'll automatically encapsulate it in a C group. When you run systemd kill, it doesn't rely on any PID files or anything. Since it's in a C group, it actually nukes the entire C group. So even if your application double forks or quadruple forks, lots and lots of processes out, and they essentially are no longer parented correctly, it's fine. It will clean up everything that was ever forked out of that C group. Right. And so what we're going to do here is, this is a service file that would run under a regular systemd system, but we also have this additional section called xfleet. It now has been simplified. No, it is still xfleet, which means this is a service file extension. In particular, it's for fleet. And it has just one entry saying global. So since this is our log exporting daemon, we want to export all the logs from all the hosts to this hosted service. So we'll do fleetctl start, and then this thing. And what should happen is that this will land up via the fleet's API inside of etcd. Each of the fleet agents running on the host, remember we told each of the hosts to be running fleet.service. Each of those fleet agents will notice that there's been a change in their configuration, and then they will start running the service. So if we do fleetctl list units, we should see that the thing is started. Right, so you'll see that each of those services is active and running on those individual hosts. And then if the internet is still working, yes?
Did you say that systemd is actually interpreting this, or the fleet agent is acting as a systemd?
So yes, this is a good question. So what's happening is that the fleet agent is looking into etcd, essentially, and it's checking for any work that's been assigned to this individual machine. So node 1 is checking the node 1 work list, and it's saying, oh, is there stuff in that list that I'm not running? Okay, I will tell systemd, you need to run this service file. So it downloads the service file out of etcd, and then tells systemd on the individual host, run this. And then it reports the status of that process, like if it's running and active, back up into etcd so that the cluster sees, yeah, I've requested 5 of these things, and those 5 things are running, in fact. And that's where this metadata is coming from. And then you can do all sorts of really adorable things like SSH, fleetctl SSH. This is one of the reasons Go is awesome, because they implemented a full SSH client in Go. But based on the metadata stored in the Fleet API, I can do things like fleetctl SSH and then one of the machine IDs from Fleet. Or if individual hosts are running, I can do fleetctl SSH and then the name of a service file. Let me make sure I didn't lose my terminal. Okay. Yeah.
Just very quickly, you mentioned that you're actually able to store the file on etcd, and that's including the example that we used to sort of key values.
Yeah.
What's the simplest example of using it as like a key, essentially file storing and uploading simple things in?
I don't think I follow. So the use case is that you store anything that you need to have as configuration in etcd. And so storing ASCII text is a perfectly good configuration format. So I don't think I follow your question.
So this stored the entire text of the systemd file.
Yeah.
As a single value.
Yes. Yeah, that's what we do. So we have, so the question was how do we store these service files in etcd? And the answer is that we have a list of all the service files that have been uploaded by users, and those exist as essentially an etcd directory. So they're prefixed. It's like coreos.com/fleet/service files or something. And each of those service files exists as its own key. And then we point to those and tell machines you need to be running X name service file. Yes.
Hi. So the dependencies of fleet and the underlying worker are both talking essentially indirectly via etcd. Is this correct?
Yes, that's how fleet is implemented. So the fleet agents need to have access to the etcd server.
Right. So essentially, by setting and updating values in etcd, they're communicating with each other.
Right. Well, so there's no horizontal communication within Fleet. Essentially, all that happens is we leader elect a single process called the Fleet scheduler, and then we have every machine runs the Fleet agent. And so the agents are just dumb, and they are doing this loop where they look and they say, what should I be running? Am I running that? No. Start the things that I'm not running. And the Fleet scheduler accepts API requests. And then based on what the user has requested, so the user requested, in this case, 5 of these journal offloader thingies to run. Based on those requests, it farms that work out into individual machines' queues, and then those machines are just, again, looping, waiting for work to land on them. And then if the scheduler notices, hey, somebody requested 5 of these things, but only 4 is running, it'll choose a new host and assign the work to that host.
Right. So these agents are using systemd to spin up
Yes.
C group or Docker containers, however you have it configured.
Correct. Yeah. We thought this was a really convenient abstraction, this idea of using systemd services, but then giving you essentially leader election and replication of services for free without having to do any more work than take that exact same service file that runs on one host and then run it on lots of hosts. Yes?
Cool. So in the example you've just run, the fleetctl journal, blah, blah, blah,
Yeah.
service, that started on all of your hosts. Did that start on all of them because the global equals true?
Yes.
Okay, so I could have said, some other thing and it would have started on 5 of them. Or
Right, exactly. So what we use, the pattern that we use if you want to start like 5 of something is we'll...
You've already got 5, so 3 is there.
Right, yeah. So the pattern that we use is we do like expansion. So we'll do something like this. We'll talk about how other systems do it. So the other examples in this talk will be around Kubernetes. And Kubernetes has a slightly different way of doing replication of a single service. But this is a systemd pattern of essentially doing a templated unit. So you say whatever the name of your unit is, and then @, and then some identifier.
Okay.
Yeah. All right, everyone on board? So hopefully if logentries.com is working right now, we should be able to see some log data streaming in. Woohoo! So we have real-time log data coming off of these hosts. And looks like people are trying to hack these servers. Perfect. Getting invalid SSH logins for user XBN. Awesome, perfect. So our machines are actively getting hack attempts, and we're able to see that in some sort of centralized dashboard. And we used a single service file and Fleet to farm this out to our entire infrastructure. Right. So, and it was this file that did it. And this, in particular, this Docker, this container that is running the agent for the log entries hosted service, and then it's talking to the systemd journal socket to actually get the logs off the host. Great. Right, so those are running throughout the infrastructure. Now, another common question that we get about CoreOS is where are all of my system administration tools? One of the things that CoreOS does not do is it does not have a package manager. We believe that containers provide all of the utility of package management, but free the individual operating system vendor from having to ship and snapshot all of open source at a given time. And there's some nice fallout from this. Since we're freed up from having to snapshot and ship all of open source, we're able to concentrate on the pieces of code that we think are important and that are required to get your application running. So this is things like your container runtime system, SSH, and the kernel, most importantly. And these are the primary things that are inside of CoreOS, are these 3 components of SSH, the kernel, and a container runtime system. All right, but we do have this cute tool called Toolbox that we wrote. And what Toolbox does is it downloads a base image of whatever operating system you'd like to have. By default, it downloads the base image of Fedora. And so it downloads that base image and then extracts it to disk. And then instead of using the Docker runtime, which doesn't have a very granular way of deciding which namespaces I want to have access to, it uses systemd nspawn in the background so that we have that we are running in a container that has access to most of the host resources, like the process ID namespace, the network namespace, and a few other pieces. And so what happens is that we've now been dropped inside of a Fedora environment on top of this CoreOS host. And so one of the things that you often want to run is like TCP dump on a host. Obviously, we don't ship that because we don't have a package management system. But you can imagine that, and one of the other things that Toolbox does is it enables you to create, why is it not downloading? Yes. It enables you to create things so that say you have 2 users or 2 sysadmins in your environment, Joe and Sally, and Joe really prefers Debian, but Sally has worked in a Fedora environment for her entire career. You can use Toolbox so that when they SSH into the CoreOS host, they get whatever their preferred sysadmining environment is. And so they can use whatever tools they're used to using. They can use their Emacs, whatever, et cetera, all within essentially a sysadmin container. And then you can clean that whole mess up when they leave. So it just nukes the entire container's root file system when they log back out of the host. So you're left with a consistent environment again. Essentially, this is solving the problem of like every single host that you log into is slightly special because that sysadmin left behind their Emacs configuration that one time, and then they forgot that they installed GCC because they needed some special network debug tool, and et cetera. It kind of solves that problem. So what we'll do as just a demonstration, it's called Toolbox. It's a really simple, like 40 lines of code, but it integrates systemd nspawn and Docker. So we download the Docker image and then use nspawn. And then apparently they removed IP route from the base Fedora image, so I can't run IP. Super minimal. Okay. So what we have is this flannel bridge, and so we'll start to dump all the traffic that's coming across our flannel overlay network bridge, and then we'll log into another host here, and we'll do ping so that we can see that the TCP dump is actually running as we would expect it to be running. Of course, I lost my terminal. Node 1. Oh no, where is it? Right, so we have a ICMP from, I'm not actually pinging the right address actually, but you get the idea. Essentially, we're able to do things, administrative things like do a TCP dump, et cetera, from one host that has no tools installed, and verify that like networking is working, et cetera. Any questions on Toolbox or the utility there? Yeah.
You log out and the Fedora stuff disappears.
Not automatically. You can do that. So if
I mean, you're saying it cleans itself up. When can you do that?
it doesn't, you can though. Essentially, the question was, you said that the Toolbox automatically cleans itself up. Essentially, it's just a static file system. So I think it's var lib toolbox. Yeah. So it's the name of the user and then the name of the environment that they want to run in. And so you can imagine having a cron job or something that would just nuke this directory every once in a while.
Okay.
Yeah.
So it builds a container that's running the shell and all that sort of stuff,
Yeah.
but the file system's safe.
Right. And it's mostly just a hot cache. So if Joe or Sally logs back in, their tools are still on that host. but you'd want to definitely set up some type of timer or something to clean that up. Yep. Any other questions about Toolbox or the utility there, or how you can use sysadmin tools on a minimal operating system? Or any other questions on how that works? Great. Okay, so what we're going to do now is I wanted to show other sorts of schedulers running on top of CoreOS. And who's used a scheduler-based system or is familiar with schedulers in general? Okay, that's very few hands. So I'll do a couple of slides just so everyone's on board and knows what we're talking about when we talk about a scheduler-based system. All right. Present. Okay, so we talked about containers a bit. We talked about CoreOS and the reduced API contracts there and how they do stuff. The next piece is clustering, and this is where the schedulers come in, and this is where we start to talk about designing infrastructure for individual host failure. And the first piece of that is etcd, where all that stuff's stored, but the other piece is scheduling. Essentially, scheduling is about getting work to servers in a manner that doesn't involve human beings saying, I have 5 servers, I have 4 services, how am I going to map this out? And not having to drop down to Excel spreadsheets or README docs to map things out to machines. So selfishly, it begins with you, because you're special and the universe revolves around you. And the computers should be doing the work that we want them to be doing. And so you have a request for the computers saying, let's say we have an infrastructure of 50 hosts. I have a service running it that's already been built inside of a container that is able to handle 5 requests per second. And I know that my load is going to be 100 requests or 500 requests per second. So I need 100 of these things running, these processes running, in order to handle the load that I expect. So you describe in a document, hey, make sure these 5, this thing is running, and make sure that enough of them are running, 100 of them are running. So you describe that in a JSON document. I need 100, and I want it to be this application. The scheduler then has this active loop. The active loop is, what did the user tell me to do? It told me to run 100 of these things. What's the current state of the system? 0 is running. What's my to-do? I need to have 100 of these things running. All right, what's the list of machines that are out there, and what's their capacity? What sort of resources do they have available? All right, divide this 100 things up across those machines. In the case of 50 machines that are completely unloaded, ideally it's 2 per host. And then the machines get this manifest of, you need to be running these 2 things, you need to be running these 2 things, et cetera. And this is the basic process of a scheduler. And this is how things work internally at Google for almost all of their services. They have a system called Borg. This is how things work at Twitter. They use an open source project called Apache Mesos. And a lot of these organizations that have a lot of different engineering departments managing a lot of different pieces of infrastructure, one of the large expenditures in their environments is the capital expenditure of buying servers. And so they don't want every time an engineer comes up with a new crazy idea to then have that engineer go off and spend 10K on new Dell hardware, as much as that is a fun thing to do. And we all enjoy looking at shinies. It is not a very effective use of either the developer's time or capital resources of a company. And so these schedulers have emerged because it frees engineers from having to think about capacity in terms of racks and servers, and think about capacity and what does my application need, and then I'll just tell the environment, make this happen on my behalf. Everyone get that? Okay. And so what Kubernetes is it's the scheduler. Fleet, the tool we used earlier, is also a scheduler. But Kubernetes adds a bunch of things around doing automated rollouts and canarying, et cetera. And then service discovery is a big part of Kubernetes. It kind of defines how service discovery should be built. So it's a much higher level set of tooling than Fleet is, where Fleet is trying to be systemd for lots of hosts. Kubernetes is kind of providing a lot of primitives for how you might run web scale infrastructure. All right, so there's a number of moving parts in Kubernetes. The first is the kubelet, and so we'll start this this unit file. Need to be on the actual host. Here we go. So we'll start this this unit file for the kubelet, and the kubelet is just like the fleet agent. It runs on each host. So that's why we're using a global unit again. It runs on each host, and it watches for work and executes it. The next piece is the proxy. The Kubernetes proxy, it exists on each individual host, and it's used as a mechanism for service discovery. So it, we'll talk about labels and services later, but the basic idea is that within my environment, if I hit a particular port and IP address, no matter what host I hit that IP import and that IP import on, I'll be redirected to wherever that service is running, and that's via a reverse proxy called the kubelet or the kube proxy. The next piece is that I'll be running the API server. This API server is going to be running only on my control node. So it, as an example of how like fleet services work, we have this role equals control. And so it ends up landing on just the control node. And this is the HTTP service that I'll actually be talking to in order to make Kubernetes API requests. There's the controller manager, which deals with replication controllers, which we'll talk about in a bit. There's the scheduler, which is the piece that actually takes work that the users requested and transforms that into lists of work that the individual kubelets will execute. Again, that'll run on the control machine only. And then the last piece is a thing called Kubernetes register, which takes metadata about the hosts that exist within CoreOS and uploads it to Kubernetes, so the Kubernetes API has access to all the same metadata that the CoreOS host has. Mostly it's about what the networking topology is like at the moment. So with those services, we should, with any luck, have a fully working Kubernetes stack, and we should be able to see them within Fleet. Looks like everything's active and running, so fantastic. And we'll be using a command line tool from my laptop called kubeconfig. This tool has been replaced by a new tool called kubectl, but kubeconfig is what this tutorial was written against, and kubectl is like a month old and way buggier. So I'll stick with kubeconfig right now. And so what's happened is that very similar to how FleetCTL has list machines, kubeconfig, they used to be called minions, but they've renamed them to kubelets, but the name still sticks around. So this is listing all the worker nodes within the infrastructure. So we have these 5 worker nodes, and those are nodes 1 through 5 that are these CoreOS VMs. Everyone on board? So this is our compute infrastructure. And this is all being talked to over an HTTP interface. Kubeconfig uses an HTTP interface. I'm SSH proxied into the control node, and that's how how kubeconfig is actually working and talking to the infrastructure. Okay. So what we're going to do here is we're going to deploy a application. Actually, let's back up for just a second. Who's here built a Docker container before? Okay, it's about half the room, which makes me a little nervous. So I'm going to give a quick 3-minute digression on how to build a Docker container, just so people are comfortable with the concept of an application running in a container. I have a host over here that I've been using for Rocket development and testing out on Ubuntu. But this host has Docker installed and a Go environment. So this virtual machine, on this virtual machine, I have Go installed, and I have this really simple Hello World application that exposes an HTTP endpoint. Okay, and so what I'll do is I'll build this Go source code, and I'll build it as a static binary, so it has no external dependencies. And so on any Linux host, this will just run without libc installed or anything. You can literally just like make this the initRD from the kernel. But this is the binary that'll actually come out of this, is hello world. And if you run file over it, it'll say it's an ELF 64-bit Linux binary. Okay? And then we have this Docker file. And the Docker file is the way in which containers are built within Docker. They can do really sophisticated things like building the source code, etc. But for the sake of this tutorial, we're going to do the really simple thing, which is we're going to say, again, Kelsey Hightower made this. I'm Kelsey Hightower. We'll say, like, this is the maintainer of the thing. This is the from line here is the root of the container, and the scratch container essentially is a completely empty file system. The maintainer is Kelsey. We're going to add this binary, this hello world binary, into the container, and it's going to be called /hello world. We're not going to put it anywhere fancy. We're going to tell the system that it's going to be exposing a single TCP service on port 80, and that when you want to start the container up, you're going to execute /hello world, and that's the entire metadata for this container. So I'll run docker build -t wait.io Kelsey Hightower hello world. Yep. And so what this will do is it'll take this Docker file, it'll take the binary that we've already built, and then it'll create a container from it. And then I'll run sudo because apparently I didn't set the group properties correctly. And then after doing all these steps, it'll tell me what the container, the image ID is. And then I'm able to do sudo docker run quay.io /Kelsey Hightower what do I call it? Hello world. Okay. Uh-oh. Maybe I didn't call it that. Oh, shoot. Okay. Live demos are hard. Okay. So this will start up the process, and then I should be able to curl it, I hope. Uh-oh. This is bad. Oh, I know what I did wrong. Typing is so hard. I used to have a linear algebra teacher who said that linear algebra is easy, linear algebra is easy, arithmetic is impossible.
Are you missing the cube for?
Oh, see what I'm saying? Yes, thank you. Impossible. Okay, perfect. So it's responding. We should be getting like HTTP headers back and stuff. It's just an empty body. Okay, so that's how you build a container. You can do a full stack from source to container, or you can have a pre-built binary and import that into a container. And then it essentially runs like a static binary. So everyone on board with how a container is built, you get it. You're not afraid of it anymore. It's very simple. Okay. You can imagine that these containers can be built automatically using a CI system, and like we have we pronounce it Quay because we're not familiar with the word, but you can integrate this service with GitHub and it'll automatically create the container for you, etc. But that's besides the point. The idea is that you have some sort of URL that is your application, and you tell other things in your infrastructure, run this URL. Okay, let me find my terminal again. Okay, so what we'll do now is we'll create what's called a replication controller within Kubernetes. And the replication controller is this thing that tells the infrastructure, I want X of these things running. So it's a pretty straightforward JSON document. So less. And it has a few pieces of information. The first thing that it has, actually I'll run this in Vim so you can have a cursor to look at. The first thing is we say how many of the thing we want running. This is the JSON document that will we'll make an API request against Kubernetes API for. We tell it what things it's looking for, what are the things that it's actually replicating. So it's replicating a thing called hello. It's in the environment production, and it's of track stable. So in this example, we'll have a stable track and a canary track. So we'll have some copies of our code that are running a new version of the code that are added to the load balancer later in the demo. And then there's a template of what this application looks like. And this primarily describes the container that should be ran. So we're gonna have the container, we'll name it hello. It'll start from the image that we just built, or a similar image called hello, and of version 1.0. And then we can put optionally some constraints on it of how much CPU. So we're going to constrain it to just 100% of the CPU. And then how much memory it can use, and then the actual port that it exposes as its service. And then we assign some additional labels to that application so that we can find it later, and we can find any of its other copies later. And that's the primary thing that we're going to be telling the API. I want one of these things running. You can find the code to run it over here, and then it has these metadata properties. It's going to be in track stable, and it's going to be in environment prod. And you can use whatever sort of labels you want. You may have like owner equals Joe. You may have billing group equals accounting, etc. So it doesn't, these things are just arbitrary, but you kind of have to agree with them inside of your organization. There's some recommendations, obviously, like environment of prod and dev, but they are free-form labels. Okay, yes?
Why did you have to repeat the ports? I mean, the Docker image already had.
Yeah, that's a good question. The reason that you repeat that is because Kubernetes isn't super opinionated on the container runtime. And so right now they do use the Docker stuff, but you can imagine other things. Right, so what we'll do is we'll take this JSON manifest and we'll talk to the API via kubeconfig, and we'll say, I want you to create this replication. They call it a replication controller. Essentially, I want X of these replicas of this thing running. It's called a replication controller. And so we tell the API do this on our behalf. And so this thing is that while true loop that we were talking about, that's constantly looking, are one of these things running? No, make sure it's running. Are 3 of these things running? Oh God, all right, make sure there's only 1 running, like kill those other 2 things. And it's just doing this thing in a constant loop. So we can do kubeconfig list replication controllers and see that there's this hello stable controller, which is the name of our controller. It's for running the hello application on the stable track. And then the environment and tags and labels that it's in. And what should have happened is that since we requested that one of these things be running, it should have created a pod. And a pod is an abstraction that exists within Kubernetes. And a pod is the logical combination of a number of containers. So imagine that you have a container that is an HTTP server, and you also want to, inside of that container, export the logs to another service. Those 2 things are logically the same, like one application. And so Kubernetes has this abstraction of a pod. It's like peas in a pod, or like a pod of whales that are together. So you schedule a pod as a single unit. In our case, we only have a single container that makes up the pod, but you could imagine having this multiple containers. Another example would be like, I have Nginx, and then I have some fast CGI daemon that I have to bring up behind Nginx. And these 2 things logically are together and should be scheduled together. Everyone get the concept? So what should have happened here is that when I do kubeconfig list pods, is that I should have a single copy of these running on one of my machines. So it looks like lucky number 7207 ADD7 was the machine that got assigned the work. And it tells us that it's running on this host, what the IP address is, the IP address that was assigned out of Flannel, etc. And that it's currently running. Perfect. Now things get slightly interesting because we want to take that same JSON file that we just had, and we want to bump this up to say 4. So we have multiple we have resiliency against host failures. So we'll run kubeconfig with that same JSON file, but instead of saying create replication controller, we'll say update existing replication controller. And the kubelet agents should be looking for all that work. So great. So we see that there's now 4 of these instances running inside the environment. Awesome. Now this is interesting, but all I've done is I've splayed a bunch of processes over your environment, and you have no idea of how to talk to them. Not super useful. The entire point of this is that you like load balance something behind, example.com, and you're making loads of money. And so this is only useful if you are able to create a service. And so what happens in Kubernetes is you have the processes running, and then you take those labels of the name of the service, in our case hello, and you create a load balancer called a service that load balances all those processes behind it. So let's look at the hello service JSON file. So this says that the container port that it's looking for is port 80. It's going to expose the service on port 80. And it's looking for services named hello in the production environment. So you can imagine having a service that load balances only the development environment, or load balances prod and development together, because you want to have a mix of things, and expose them on different ports, different IP addresses, so that developers have a way of mixing these things together. Yes?
Is that, that's the health checking for the, specifies the health check that's used to...
That specifies the health check used to, verify that the services, the machines are up?
Yeah, so this is a simple TCP reverse proxy. You can imagine having more sophisticated reverse proxies, but it implicitly does a health check because it's a reverse proxy. So if it tries to proxy you to somebody who's not up, it'll get a connection refused and it'll choose the next one. It's like HA proxy or something. It's a round robin load balancing TCP proxy. But again, you could imagine using the API and exposing an HA proxy service instead that then load balances the things behind it.
That's is it the control node that's doing the that appears as the load balancer?
No, so this load balancer will end up running on each individual host. And so this is so that you can have access to all the exposed services within the environment. And it's getting a little more sophisticated within Kubernetes. They have the idea of a portal, and so each service will get a unique IP assigned out of the IP space, and then have the port attached to it, and that combination of things is called a portal. And that essentially is a floating IP in the environment, and you can always talk to it, and the network is in charge of ensuring that you're able to talk to that thing. So this is the most simple implementation of services, but you can imagine more sophisticated things that use virtual IPs and that sort of stuff.
So the virtual IP is just going to move from machine to machine? Is that
well, the individual worker machines are in charge of ensuring that the hosts have a route to those virtual IPs.
Okay.
Thanks. Yeah. Yes.
It's okay, I don't know the speaker. But could you just give us a recap, because you've covered quite a lot of ground here. So you've layered CoreOS with
Yes.
ECD
Yep.
running fleet,
Yep.
fleet control and a fleet agent.
Yep.
You've got a control node and you've got worker nodes.
Mm-hmm.
And then on top of that, you lay Kubernetes,
Mm-hmm. Yeah.
which is laying down a whole lot of services, service proxies, and a whole lot of other stuff I can't remember.
Yep.
And now you're exercising all this infrastructure.
Yep. Yeah. So that
A diagram of that?
yeah, I don't have one built up. I wish I had somewhere to draw it, but
There's just an awful lot of moving parts.
yeah, I completely agree. Right, so we can kind of break it down. So we have the CoreOS is the underlying Linux operating system. It really does nothing interesting. It has SSH in the kernel. Okay. Then we have a shared configuration store across 5 hosts.
ECD.
etcd. And so etcd is where all these hosts are able to share a key value namespace. So you're able to write simple JSON documents, et cetera, into this namespace, and people are able to watch for changes. Okay. On top of that, we have two schedulers. We have a very simple scheduler called Fleet that looks like systemd and allows for this abstraction of global services. So I want to have my log aggregation agent exporting logs off my host. I want to allow for this Kubernetes agent to run on all my hosts so they can download work. So it's a very simple scheduler, but it gives you a few primitives that are very useful. And then we're running an application. This application happens to be a scheduler itself called Kubernetes. And Kubernetes gives you the ability to run complex pieces of infrastructure that expose services and does service discovery, and then gives you the ability to do these automated replications of simple, scalable, horizontally scalable services. And that is running on top of the CoreOS host along with the Fleet agent itself. And so this is essentially the target application for this CoreOS host. So you can imagine other schedulers being ran. We have users that run Mesos on top of CoreOS, just using Kubernetes as an example of an application that can be ran on top of CoreOS that's more sophisticated and gives you something that looks close to the sorts of infrastructure that a lot of us are building, which is 2, 3, or like a 2-layer application where you have an HTTP tier and you have like a database tier. This is the sort of application that Kubernetes is designed to run for you and to enable the system administrator to run efficiently in their infrastructure. Yes?
So then the other missing piece was Flannel.
Yes.
So is Flannel just a temporary solution? Because you've got these proxies. Can't these Kuboots proxies, or whatever you call them, deal with the network from there?
No, so the proxies are there because we are mapping from, we need a load balancer. So we're giving a particular IP or port, in this case port 80, and we're saying this port 80 you can access, and then it's going to do a round robin proxy to everyone who's running that service. The Flannel is about, I want to have a overlay network so that each of my containers are able to talk to each other across the network without having to take into consideration they're in a container. They act as if they're just any normal Unix process. And so if they get an address of 10.244.391, it says, oh, I can just talk to that guy and my packets get routed. I don't have to figure out like port mapping or anything like that. So, and you can imagine that in an infrastructure where you have a software-defined network or you have good networking gear, that you could do this without something like Flannel. But in a lot of cases, we're running in very constrained network environments, and so you need to overlay a more sophisticated thing that allows for a single host to hold on to lots of IPs. So it's Flannel is taking care of the layer 3 overlay network, and then Kubernetes is taking care of the load balancing of lots of things that are running in your environment to a single IP port combination.
So you've got the separation between infrastructure and application.
Exactly. So the proxy is all about application. So you can imagine taking this service and load balancing it, or even putting it into rotation on your DNS endpoint. Whereas the overlay network's only for internal communication between the containers. Yeah.
Regarding Kubernetes, why did you choose with the 4 replicas? Why did you choose to put 2 replicas on the same node?
This is great. So his question was when we did list pods, it looks like 2 of the replicas ended up landing on the same host. So there's 160.102. Got 2 of the processes. And this is because the Kubernetes scheduler is really unsophisticated. It just kind of makes a best effort to spread the load around. There's an integration with the Mesos scheduler if you want like a really sophisticated bin packing scheduler, and they're working on that. And then they're working on making it less, because essentially this is the worst possible scheduler, and they're making it so that the default implementation in Go isn't the worst possible scheduler, but at least does some heuristics. But this is just the current state of it. Kubernetes is a pre-1.0 project. I think they're planning on it being closer to 1.0 in the next 3 to 6 months. Right, so we have this, this hello service file. Again, we're going to define this proxy that load balances all these hello services that are now running in our infrastructure behind a single port 80 endpoint. So we need to do two things. First, we need to enable TCP port 80 on our firewall rules on our virtual machines. I should have done this in the beginning, but okay, well, I forgot to delete the old rule, so hopefully that still is working with our new VMs. And then we tell kubeconfig that this JSON file, we need to create this service endpoint. And then what should happen is that I'm able to list these instances, and I'm able to hit one of them on port 80. Yes, yes. And what's happened is that we've what's happened is that this service is now exposing in a round-robin manner all of the instances. Now, that's not super interesting quite yet because everyone's running the exact same version of the code. So no matter how many times I refresh, it's going to look identical. I'm always going to get the same response. So let's do something slightly more complicated. What we're going to do is create another replication controller called the Canary replication controller. And what this is going to do, we're only going to have one of them. It's going to be on a track called Canary, so it's going to be slightly different. And how Canary tracks are used in a lot of infrastructure is some developer has said, I know 100% that my code is 100% correct and it won't break anything. And the operations people say, let's measure that. And so what you'll do is you'll take the new version of code, which is 2.0, and then you will add just a few of these to the environment and see how it behaves behind the load balancer, if its performance is correct, if it's still handling the same number of requests per second that the old version of the code was running, et cetera. So it's essentially a way of tagging things like canary in a coal mine, of tagging things that you'd like to test out. Okay, so we'll take this this new replication controller, which will run beside the old replication controller, and you'll notice that it has the two important tags that are in our service file of the name being hello and the environment being prod. So it'll be load balanced in with everybody else, but it'll have a different track, Canary. So we'll list the pods, and we should see one of these here. This guy is running on the Canary and running the new version of our code, our 2.0 version of this Hello World application. Okay. And so what we can do now is we'll test out that this round-robin service load balancer is actually a round-robin service load balancer. So we'll do a while true loop, and every 2 seconds we'll make a new request. And so the first request we get 1.0, the next request we get 1.0, next request we get 1.0. Now I'm getting a little nervous. The next request we get 1.0. Oh yes, okay, there's 2.0. So since this is a super dumb round-robin load balancer, what you'll notice is that it's fully deterministic, and then the next one will be 2.0, hopefully. Uh-oh. Okay. Well, yeah, live demos. There should be a 2.0 in there somewhere. Let me see if the thing's still running. Oh, there it is. It's on top. Well, in any case, oh, there we go. Okay, so I guess it's not as deterministic. Maybe they fixed it. So it's not deterministic, but it is still a round-robin load balancer. Right. And so this service, because it used these labels, and it made this query of give me all the running processes that are called name and environment prod, and then load balance them for me. It made that query. It doesn't care that this particular process has the track of Canary. You can imagine that if you're wanting to kick out everybody who's trying to do canary experiments within your environment, that you would want to specify the track equals stable. Okay, great. So now that's all working great, and we have this replication controller that's taking care of our canary track, and we can update these two things separately. So this canary JSON file, we can update it with multiple replicas. We can change the version to 3.0 or 2.0.1 because that bug was actually there in the code that the developer promised wasn't there. And we kind of can roll out these two things as separate entities within the infrastructure and give different people, different organizations control of these things. All right, the last thing that I'll demo within Kubernetes is a rolling update. So as we all know, infrastructure is not static. After we deploy a piece of code, we are always planning on deploying the next piece of code at some point later. So I will leave this, this little curl thing running. Oh my gosh. There we go. Okay. And so we'll spin up a new piece of code called a rolling update. And what rolling update does is it takes an existing replication controller, in this case our hello stable replication controller, and it in lockstep I believe every minute, what it will do is it'll go through and change one of the instances within that replication controller in the stable thing from 1 to 2.0. So we have this command line that says update the image of this replication controller, this hello stable controller, from from whatever it is right now to 2.0, and then use the rolling update algorithm. This is simply a 40-line go while loop that every minute makes a single API call to the Kubernetes API to slowly update individual copies inside the replication controller to the new version. So you can imagine that you can implement this any number of algorithms. You could hook it up so that the product manager can send an email that updates a single copy, or you can do it via IRC, et cetera. Yeah?
The connection failures that you're getting there, is that not doing the health checks, or that's...
Yeah, that's probably because as I start my HTTP connection, it's nuking the process, and then I don't get an HTTP response. And this is because the service endpoint isn't really application aware, and there's code that's being landed in Kubernetes right now that you can back-end services with like Nginx. Again, this and any application-aware load balancer. So you can imagine having a MySQL-aware load balancer or an Nginx or like an HTTP-aware load balancer. Essentially, as you move further up the stack and you want to have guarantees on requests returning from some sort of request response protocol, you need to have a smarter proxy than just a TCP proxy. Right, so over time, over the next couple minutes, what will happen is that this rolling update will change all of the requests from 1.0 to 2.0. And we can actually see that happening if we run this, which is watch and then config list pods. And we'll see that four of the instances have been updated to 2.0, and there's only one instance left that's running 1.0. And so in the next minute, the last guy will be nuked, and then we'll be fully upgrading our infrastructure to the latest version. And again, like I said, this is just a really simple example that uses the API. You can imagine something that updates one person and then checks health monitoring and then waits for any tweets about your website being down, and then requires a product manager to send an email saying everything looks good still before rolling out the next one. And these are all workflows that we kind of end up implementing anyways. But the Kubernetes API, because it's focused on this idea of having a consistent piece of code that helps you roll out the update, it's actually fairly trivial to do this more complex workflowy, however your company does stuff sort of thing. All right, so that officially ends all of the demos of this stuff. Woohoo, we're running 2.0 everywhere. So I'm happy to talk about and dive into any of the moving parts further, take random questions about CoreOS or containers or anything, whatever you'd like, and that's whatever's at top of mind. And I'd like to point out that you should be able to replicate all this stuff. All this stuff was started out of a clean checkout of this repo. It includes all the JSON files and YAML files, et cetera, and the instructions that I essentially just copied and pasted, except for my typos that I introduced all over the place. So if you want to try to do this at home, all the resources are here, and you can hit me up on Twitter or email if you want to try to do it too. Yes?
Just while you've got the example running that you had before, where all of the pods were on 2.0, not the screen you just had.
Oh, yes.
So it kind of occurred to me, you started off with 5 of them running 1.0, and they were running on certain hosts and all that sort of stuff.
Right.
Did we stop the 1.0 ones and start the 2.0 ones on the same host, or did we just like stop them and then have Kubernetes go, oh, you said 5, I've only got 4, and it just sprays it across again, and there's no guarantee that they're...
Yeah, it makes a new scheduling decision.
Cool.
Yeah, yep. And the reason things are bouncing around is just because it doesn't order things coming out of the API. Yes? Oh, so,
She's running around with
okay, sorry.
Okay. First.
Yes, please.
I've got sort of 2 questions. How easy is it for rolling upgrades? How easy is it to roll back if you find something starts throwing errors and you have to quickly roll back?
Yeah. Well, I mean, we can try it out. I actually haven't tried to go backwards before, but it should work. And then I guess if I remember correctly, the command line flag is -u. Nope. I think it's -u somewhere. Minus one of these flags, -u10. Essentially, you can use the exact same idea, replace the image with whatever your old image was, and roll the update to the old version. I'm pretty sure I got the command line flags wrong, but you get the idea. It's the same idea.
And the other thing I was going to ask, do you see any sort of conflict in Fleet and Kubernetes? And is there any plans to take the really cool features of Kubernetes and merge them into Fleet, so you can sort of cut out that part of it?
Yeah, it's something that we've definitely, see, the 1.0s are coming back on the, Fleet, part of the problem is just the way the user interface of Fleet is designed to be systemd. And systemd doesn't handle service discovery, it doesn't handle the idea of replication controllers. So it's, the user interface design that we've made around Fleet is that it is systemd distributed. And it's a really useful abstraction, and it helps people take things that are working well. And always the hardest part of scaling a distributed system is going from 1 to 2, because that's where everything changes. And so we thought it's useful to have that abstraction. Kubernetes is doing its own thing, and I think that's okay. And we already have 2 schedulers within CoreOS. We have the locksmith scheduler that handles rolling out of updates within an infrastructure, and then we have the process scheduler, which is Fleet. And so I think as people start to think in distributed systems in this way, a proliferation of schedulers is okay. Yes?
As a database geek, one of the primary things that I haven't been able to quite wrap my head around with Kubernetes and then either being introduced to Fleet is how you would manage a group of machines with a single master.
Yes.
For a database, where which machine was the single master would change.
Yep. So this is something that's been an ongoing discussion within Kubernetes. And there's a few pieces of the puzzle that need to be solved. The first is that Kubernetes scheduler needs to be aware of the fact that moving databases is expensive. And so we're taking the scheduler API there's designs going on about hinting the scheduler API to say, say I'm upgrading from Postgres 9.1 to 9.2. I really, really, really would appreciate it if that 9.2 landed on the same host where 9.1 was running, because the WAL file's hot there and like everything is hot on that box. And so that's the first piece, is just being able to update software, etc. The next piece is actually how you do the replication of things. And I think that a lot of the existing Postgres tooling or MySQL tooling or whatever can be integrated well, because a lot of them are a master and slave replication sort of setup. And so you can imagine that writing a leader-follower replication that is in that is aware of the Kubernetes scheduler would be a fairly powerful abstraction to build on.
Yeah, I mean, I guess, so where I'm going with this in terms of specifically the Kubernetes configuration is that, you know, you do your initial setup and you've got one machine that's in the master role and has a specific virtual address via Kubernetes as the master, and then say 4 machines that are in the replica road and have and that's important because you have application traffic that specifically only goes to the replicas.
Right.
Well, then you lose the master virtual machine. And so you want to promote one of those replicas to now being a master.
Right.
And I haven't been able to figure out anywhere where I can actually change the role of an already running machine.
Right. So Kubernetes right now, there also has been talk about having an API for doing a leader election inside of Kubernetes. Right now, there's no API for that. Essentially, what you'd have to do is what actually Kubernetes itself does, is it uses etcd to do the leader election, because etcd is designed to do leader elections. And so the Postgres pod or container would have a little agent running inside of it that would be etcd aware, and it would be trying to do a leader election constantly. And then once it acquired that distributed lock, it would talk to the Postgres local port and say, you're now the master of this cluster.
Is there any way to extend that leader election process? Because there are obviously things inside Postgres that determine which one should be the master.
My understanding was, I could be completely wrong, that Postgres didn't have any sort of consensus algorithm or like leader election algorithm internally. It relied on something external.
Yeah, no, but the issue is that some of the replicas can be further ahead than the others.
Oh, yeah.
And you want the furthest ahead replica to be the new master.
Yeah, so what would happen there is you'd have to periodically also have the Postgres replicas either cross-chat and gossip where they are, or register themselves into etcd, like I'm at wall position XY or whatever. So we can talk further about the design. We prototyped out kind of a really bad version of this, of like Postgres master election using etcd, but I think it'd be helpful to have a discussion about how to do it correctly.
I've got the microphone. Over here.
Oh.
Yes. It was a bit alarming to see the outage happening there. And, if I was running services that where, outages are not allowed, would I need to use that locksmith thing? Or, how would I avoid that kind? I wanted to do updates without getting an outage. So how would I do that?
Yeah, so the way you do it is you have to have a load balancer that's aware of the protocol, right? So like if this had been Nginx or something, you wouldn't have seen that, because Nginx wouldn't have returned from a reverse proxy a request that was terminated halfway through, because it's aware of an HTTP request needs to be completed all the way through the full content length. And
Okay, so I need to have something perhaps like HA proxy or something that really is doing the verifying that the service is...
Yeah, and people have prototyped that. I just didn't demo it here. So there's our prototypes of using the Kubernetes API and using HA proxy or Nginx, something that's protocol aware. That's what you have to do. Yeah.
Just for posterity, in the node.yaml file that you covered earlier, just for when I'm coming back to this and watching it later on.
Sure.
You had a flannel definition section in there. You were saying that that's not quite how you would do it maybe tomorrow, or
Yeah.
I'll come back to this in the future.
Yeah, so
does that just become like the other declarations for etcd and fleet?
Yeah, exactly. So this is the doc that we just did. If you want to know the background, like the historical background of why we had to do a lot of work to make this work correctly, because we're essentially wanting to run Flannel in a container, but we need to configure Docker, which is our container engine, so we end up with 2 Docker engines running. Anyways, it's a long story. Really interesting, but a long story. But instead, you can just say start Flannel, and then here's the network, which removes like 100 lines of boilerplate, and it actually uses a container instead of like W getting things from the internet.
Back to the previous question about HA proxy and using Nginx instead as the load balancer. Then what's the actual preferred use case, or when would you want to use Kubernetes built-in proxy?
I missed the last 3 words.
What is the ideal use case for the actual built-in proxy service inside Kubernetes, rather than going to HA proxy or Nginx?
Yeah, the primary use case is simplicity. So if you don't want to build something harder, and so for a lot of things this works fine. So Memcache, Redis, like things where your driver will actually be aware that you didn't get the full thingy that you were expecting to get back. It just depends. Yeah, essentially, there's a lot of use cases, and it's really simple, and it's built into the thing, so you don't have to think about it. You could also imagine like APIs that are internal. Like if you don't care that you're not going to, if you'll get a truncated response and you can handle that. Like a web browser won't handle that too hotly, but internal things will be aware that they didn't get the full content length, give you an error, you handle that inside your code as regular due course. 5 minutes. Yes?
Just overall, like Google has a very sophisticated scheduler in Borg, which is using to run things at huge scale. Why is it overall that a lot of primitives that are coming into Kubernetes are so much simpler, and a lot of these decisions don't seem to be ironed out, whereas you would expect over the last several years that they have actually worked it out internally? Is it just completely separate teams?
A lot of the people that you see working on Kubernetes are the teams who worked on Borg and Chubby inside of Google. The reason is because the hard, like scheduler, writing the scheduler is actually the easy part compared to everything else when you think about it. Because what we're trying to do is get consensus around APIs, and that's the most impossible like problem. It goes back to like arithmetic is impossible, right? It's because once you define an API, you're going to have other third-party application writers using that API. You're going to have tooling like kubeconfig or kubectl. You're going to have dashboards, et cetera. And so the first thing you have to do is get consensus around that API. Then making a really efficient scheduler is easy because it's on the other side of that API. And so given the small team that's working on it, they wanted to nail the API. They wanted to nail the interactions. They wanted to get all the use cases of load balancing and replication correct first. And then you can go through and take advantage of all of the infrastructure you've laid out to do an efficient bin packing and utilization of the resources. The other reason is there's already really good schedulers out there like Mesos, and so you can imagine replacing the dumb scheduler that I used with an existing open source scheduler like the Mesos scheduler too. Because people do use the Mesos scheduler in infrastructure today and get really good utilization, 60–70% of CPU, RAM, and disk that they buy from their hardware vendor. So that's the primary reason. They're extremely good team. It's just it's not the nut of the problem. Yes.
I asked a question about the application. So if we use round robin with the stateful application, because this demo is about the stateless application, right?
Right.
So what about the stateful application like we use a JMS or any others like session management and other stuff? How we use this model on like scaling, create multiple bots, and then how it's scale, and then how managed in the application level?
Yeah, it goes back to the question around Postgres. Essentially, there's two parts to the answer. One is that the Kubernetes guys are designing as well as they can be for existing data stores like Postgres and MySQL and these leader election patterns. The other answer is that in a lot of cases we have infrastructure that we buy that already handles the stateful bits of our applications pretty well. So like from cloud vendors, you're buying a SQL database or whatever, or we run a large database that holds onto all of our application state. I guess there's a third answer. The third answer is that people are working on more sophisticated databases that are designed for doing this sort of, that expect host failures as the normal case and don't have a strong leader. And so there are things like Cassandra or Riak that are sort of designed in this way, where you can, you lose the consistency of the data store, but you get the freedom that an individual host going away isn't necessarily a data loss situation. And then there's also people who are taking some inspiration from Google's white papers around Spanner and some of their other database products, where you sort of want to mix. You want to say, I need hard consistency with hard replication around these things because it has to do with money or it's some very sensitive bits of information. But then this other bit of information is a cache, or it's a replicated piece of data for this region that I'm in, and I care less that it's safely stored anywhere. And this idea of having a tunable consistency and a tunable replication is something that we're seeing in new data stores. One that I'm particularly excited about called CockroachDB, which is using our Raft implementation from etcd, and then taking inspiration from the Spanner paper to implement this key value store with tunable consistency and replication. So it's kind of a mix of answers, and none of them are that great, to be perfectly fair. But I think everyone is really focused on figuring this problem out for the variety of use cases that do exist.
One more question about SCD. What about, do we have any API access from application to the SCD durable store? Like we get some information like with machine service the request before, and then we get the information from the API.
The information?
Like SCD durable storage.
The etcd, I think I'll have to talk to you offline on that one, because we just ran out of time. But etcd does return a bunch of metadata about which etcd member like serviced the request and that sort of thing. That may or may not be what you're asking about, so we can talk about it. All right. Well, I want to thank everybody. Check out the GitHub page if you need anything. Remember, my name is Kelsey Hightower. And I really appreciate the time that you all took to come out. So thank you.